Hello students, welcome to my channel Engineering Education. Please subscribe my channel. Thank you. In this lecture we are going to solve problem 11.12, chapter 11, Rotodynamic Machinery, Applied Thermodynamics by Eastop and McConkey. So the statement of this problem is, at a particular stage of an axial flow gas turbine, the radius at the blade root is 0.225 meter and the blade tip radius is 0.375 meter. The blades are to be designed according to vortex theory with 50% reaction at the mean radius. The angle of the blade inlet at the tip is fixed, and that is 0 degree. Blade angles are measured from the axial direction. The turbine rotates at 6000 revolutions per minute. The flow velocity is to be 0.8 of the blade velocity at the mean radius, and the mean density and the blade annulus may be taken as 0.7 kg per cubic meter. Assuming the conditions required for radial equilibrium using free vortex design, calculate the inlet and exit angles for the moving and fixed blades at the mean radius. Similarly, the inlet and exit angles for the moving and fixed blades at the tip. The inlet and exit angles for the moving and fixed blades at the root. The degree of reaction at the tip and the root. The power output of the stage. So first of all, in this problem, the information given will be written here. So given data is, first of all, we have given the radius blade root, which is 0.225. so this is the radius at the blade root is 0.225 meter. Similarly, radius at the blade tip is 0.375 meter. The blades are to be designed according to vortex theory, and degree of reaction is A is 50%. Also, the speed of the turbine is 6000 rpm, revolution per minute. Flow velocity CF is 0.8 times of blade velocity at mean radius, and the mean density is 0.7 kilogram per cubic meter. We have to take and assume the free vortex design, and we are required to find, in part 1, we are required to find the inlet and exit angles for the moving and fixed blades at the mean radius. So beta IM, which is the blade inlet angle at mean radius, and beta EM, which is the blade angle at exit at mean radius. Alpha IM, which is the absolute velocity angle or the fixed blades angle at inlet at mean radius. Alpha EM, which is the angle at the mean radius at exit for fixed blades. Second, we are required to again find these angles at tip. So beta I t, we will use the subscript t in this case. We have used m for mean radius and t for tip and r for root. So beta it, beta et and alpha et, alpha it and alpha et. Similarly, third, we have required to find these angles at root, beta IR, beta ER, alpha IR and alpha ER. Also in part 4 we are given that to find the degree of reaction, which is represented by A, at both tip represented by AT and at root AR, degree of friction at tip and degree of friction at root. Fifth, we have to find the power output. So output power will be calculated in this problem. This is the general diagram of an axial flow gas turbine. This represents fixed blades and this is for moving blades. And this is the general diagram for axial flow gas turbine. CB is the blade velocity, CAI is the absolute velocity at inlet, CRI is the relative velocity with respect to the blade at inlet, CRE is the relative velocity at exit, CAE is the absolute velocity at exit, and delta CW is basically the change in world velocity, CF is the flow velocity, and it is the Y component of absolute velocity at inlet. So these angles, alpha I, this is for absolute velocity, beta I is the blade velocity at inlet, and it is the angle with Y axis which the CRI or relative velocity is making. Similarly here alpha E is the absolute velocity angle and beta E is the blade velocity at exit, which the CRE velocity is making with Y axis. So this is the general diagram. We can make 3 diagrams representing the blade root, blade mean radius and the blade tip. So at these 3 places we can draw these velocity diagrams and will help in problem solution. So now coming to the solution of this problem, first of all we will find the mean radius. So mean radius is equal to root radius plus tip radius divided by 2. We have given the values of these two radius for root and tip, which is 0.225 plus 0.375 divided by 2. So the mean radius value comes out 0.3 meter. Also the blade velocity at root is equal to 2 pi r into n by 60. So 2 pi, this value is given, which is 0.225, and the value of n is 6000 revolution per minute divided by 60 to convert revolution per minute to revolution per second, RPS. So the value of CBR comes out 141.37 meter per second. Also, to find the value of blade velocity at tip, so CBT, blade velocity at tip, is equal to 141.37, which is the blade velocity at root, multiplied by 0.375, which is the radius at tip, divided by 0.225, which is the radius at the root. So from this we will get the value of blade velocity at tip, CBT, and it comes out to 35.62 meter per second. Also, we can find the value of CBM, which is the blade velocity at mean radius. So for this, again we will multiply the blade velocity at root, which is 141.37, multiplied by the mean radius is 0.3, and the radius at the root is 0.225. So from this we will get the blade velocity at mean radius, and it comes out 188.49 meter per second. So we got these three values of blade velocities at root, tip, and mean radius. So for the tip, we know that we have given that beta IT is equal to 0 degree. Therefore, we can say that CWIT, which is the world velocity at inlet at tip, will be equal to the blade velocity at tip, and it will be equal to 235.62 meter per second. So later on we can use this value in problem solution. Also, CWIM, this is CWIT, so CWIM, which is the world velocity at inlet at mean radius, is equal to 235.62 into 0.375 divided by 0.3, and its value is 294.53 meter per second. Also, the value of CWIR, which is the world velocity at inlet at root, is equal to 235.62 into 0.375 divided by 0.225, which is equal to 392.70 meter per second. Further, we can separately make triangles, velocity triangles for each place or position. These are the velocity triangles. This one is for blade root. This velocity triangle is for blade mean radius. And third one is for velocity triangles for blade tip. Now further, we are going to analyze this problem and find these missing angles, and for output power we will also find the change in work velocity and the mass flow rate value as well. So let's first find the value of CF, and CF is equal to 0.8 times the blade velocity at mean radius, and it is equal to 0.8 into 188.49 meter per second, and the value of this comes out 150.79 meter per second. This velocity CF is constant throughout. Further, from the blade diagram or velocity diagram, that is from blade mean radius velocity diagram, we see that tangent beta Im is equal to 294.53 minus 188.49 divided by 150.79. It is equal to, when we solve this for beta Im, the value of beta Im is 35.1 degree, and this value beta Im is equal to alpha Em. Also, from this diagram, velocity diagram, blade mean radius diagram, tangent alpha Im is equal to 294.53 divided by 150.79. So when we solve this for alpha Im, so the value of alpha Im comes out 62.9 degree, and it is equal to beta Em, as it is obvious from the velocity triangle. Further, these are the angles for moving and fixed blades at inlet and exit as required in part 1. With the inlet, we have to find first the inlet and exit angles for the moving and fixed blade at the mean radius. Now we are going to find the inlet and exit angles for the moving and fixed blades at the tip. So for that, again we will find some other missing things. So first this is for part 1. For part 2 now we will find delta CW m, which is the change in world velocity at mean radius, and it is 294.53 plus 150.79 tangent beta I m, and when we put the value of beta I m here and equate this, we get the value 400.59 meter per second. Also, to find the value of delta CWR, that is the change in world velocity at root, so it comes out 400.59 into CBM, which is the blade velocity at mean radius, divided by CBR, which is the blade velocity at root. So putting the values, 400.59 into CBM is 188.49 divided by CBR is 141.37 meter per second. So delta CWR value comes out 534.11 meter per second. Similarly, to find the value of delta CWT, which is the change in world velocity at tip, and it is equal to 400.59 into 188.49 divided by 235.62. So simplifying this, we get the value 320.46 meter per second. Similarly, from the velocity diagrams, moving blade inlet angle at tip is 0. So we will write it: moving blade inlet angle at tip is 0 degree. So also from velocity diagrams at tip, which is drawn above, this is the velocity diagram at blade tip. So looking to this triangle, from this triangle we can write that tangent beta ET is equal to 320.46 divided by 150.79. I am directly putting the values. So beta ET will be equal to 64.8 degree. Similarly, we can also write from that velocity triangles tangent alpha ET is equal to 320.46 minus 235.62 divided by 150.79. So alpha, solving for alpha ET, so the value of alpha ET comes out 57.4 degree. So this angle is basically the fixed blade angle at exit at tip, which is 57.4 degree. Also, for part 3 solution, again we can write that from the velocity triangle that tangent beta IR this velocity triangle should be used, that is the velocity triangles for blade root. From this velocity triangles we can write that tangent beta IR is equal to, putting the values directly, 392.7 minus 141.37 divided by 150.79. So solving for beta IR, so the value of beta IR is 59 degree. So this beta IR is basically the moving blade angle at inlet at the root. Also again from the velocity triangles at blade root, tangent beta ER is equal to 534.11 minus 150.79 tangent beta IR. So putting the values divided by 150.79. So simplifying this and solving for beta ER, we get the value of beta ER, which is 61.9 degree, and this is basically the moving blade angle at exit at the root. Also, to find the alpha ER from the velocity triangle, again we can write that tangent alpha ER is equal to 150.79 tangent beta ER minus 141.37 divided by 150.79. So the value of alpha ER comes out 43.2 degree. So this is basically the angle, fixed blade angle at inlet at the root. Similarly for alpha IR, so tangent alpha IR is equal to 392.7 divided by 150.79. Simplifying this and solving for alpha IR, we get 69 degree, and this alpha IR is basically the fixed blade angle at the root. Similarly, in part 4, we are required to find the degree of reaction at the tip and the root. So the general equation for degree of reaction in case of axial flow gas turbine is equal to CRE square minus CRI square divided by 2CB delta CW. So this is the general equation. Another form of this equation is A is equal to CF by 2CB and into tangent beta E minus tangent beta I. So this is the general equation. Now to find the degree of reaction at tip, for that we will use CF is constant and its value is same for both tip and root. Only blade velocity at for tip it will become T, CBT, and beta ET for tip, beta IT for tip. Similarly, when we are finding the value of degree of reaction for the root, in that case the subscript R will be used, CBR, beta ER and beta IR. So I am directly putting the values. Degree of reaction at tip is equal to CF value is 150.79 divided by the blade velocity at tip is 235.62 meter per second. Similarly, tangent beta ET is 64.8 degree minus tangent beta IT value is 0 degree. So simplifying this, we get the degree of reaction value, which is 0.68, and this is the degree of reaction at the tip. Now to find the value of degree of reaction at the root, it is equal to, again this expression will be used with subscript R, 150.79 divided by 2 N2, the blade velocity at the root, which is 141.37 into tangent beta ER. Beta ER is 61.9 degree minus tangent beta IR. Beta IR is 59 degree. So simplifying this, we get the value of degree of reaction at the root 0.11. Now further, fifth, we have to find the power output. Before finding the power output, we will need a mass flow rate value. For this, first we find the area of the annulus, which is required for in further problem solution. So area in this case of the annulus, represented by capital A with subscript ANN, is equal to 2 pi RH. So 2 pi, this R is basically the mean radius, so it is 0.3, and H is the blade height, which is 0.15, so it is 0.2827 square meter. Further, to find the value of mass flow rate, we use the mean density into annulus area into flow velocity. This is the expression for mass flow rate. So putting the values, mean density is 0.7, annulus area is 0.2827, and the value of flow velocity is 150.79 meter per second. So simplifying this, we get the mass flow rate value, which is 29.84 kilogram per second. Now we can easily find the power output. For that, we have the expression m dot into delta CWM into CBM. So m dot is 29.84, delta CWM is 400.59 meter per second, into CBM is 188.49 meter per second. So simplifying this, we get the value of power output, and its value comes out 2253.5 kilowatt. So this is the required solution of problem 11.12. Thanks for watching. Please like and comment on my videos. Also subscribe my channel to get new videos.